My name is Gaurav Singh Bhati, and today we are going to present the work from our lab, experimental work on multi-agent phase balancing around polar curves with bounded trajectories. These are the contents we are going to present. As for the motivation, our main motivation for this work was safe trajectory following. What do we mean by a safe trajectory following? Suppose an agent or multi-agent system is moving on a trajectory, then it needs to be bounded from in a safe boundary such that it does not collide with anyone or does not cross any boundary. Such applications include autonomous vehicles as well as border surveillance missions. So, as per the problem statement in the experimental abstract, our objective is to practically implement the control derived in a chosen paper for moving the agents on a bounded circular and elliptical trajectories. We are referring the paper number 2 as mentioned, cited below. He is my supervisor, Dr. Anup Jain, and he has 2 papers on bounded trajectory. Our main contribution on this work is to review the existing theoretical work and analyze the methods to implement on practically in the mocap environment, and preparing the backend along with Python wrapper for unicycle model of robot in Crazy-Swarm 2, and performing the experiments on Crazy-Fly 2.1 quadcopter for bounded trajectories as the simulated trajectories below. We will be showing videos of practical implementation of these simulations. As for the experimental setup, we have a Qualysys motion capture setup with the following features. And as for the robot used, we are using Crazy-Fly with passive marker DEX, and these 3 Crazy-Flies are the exact ones we are using. The main software we used were QTM, ROS, and Crazy-Swarm 2 package in the ROS. This is a brief overview of how the communication is happening between the different nodes from one PC to another PC, and then finally to the 3 Crazy-Flies. As for the robot model, we are considering Crazy-Fly to be a unicycle model robot in which only 2 parameters are there, the linear velocity and the angular velocity. So here Vk is the linear velocity and theta k dot is the angular velocity, which is the basically control uk. And this is the complex plane representation of the urban model. For the solution approach, the referred paper has used Barrier-Lyapunov function, and using the Barrier-Lyapunov function, we can constrain the trajectories of these agents within this boundary as indicated, and they will finally come onto the desired orbit. As for the control design has 2 parts. The first part is kappa and the second part is zeta. The kappa is basically the curvature of the curve which we are following, and zeta is a control obtained in the referred paper, in which the first term represents the first term is responsible for the trajectory following of the desired curve, and the second term is responsible for the phase balancing. As for the elliptical motion, these are some equations we derived, but I will mainly focus on the experimental implementation, and this is for the circular motion, because as for the circular motion, in the ellipse there are 2 axes, minor and major axis, but in the case of circular motion, these 2 are equal, A equal to B equal to R, so the zeta is quite simple. Now coming to the main highlight of the presentation, that is the result. This is the result for the circular trajectory. In this one, the 4 videos are there. The top left corner video is the front view of the circular motion. The right one is the isometric view, and these both 2 videos at the bottom are the recordings from the QTM software. As indicated here, the proposed control law is driving the agents onto the desired trajectory as mentioned here, and they will not cross this outer boundary. However, in any case, if they satisfy the initial conditions, and the most important video is this one, in which we can actually see the boundaries, because as for the physical normal cameras we cannot see the boundary as well as the desired trajectories. This one is for the circular case, but coming to the elliptical one, that is one interesting. As for this elliptical case, you will see a slight different trajectory than a normal ellipse. That I will explain in the challenges faced part, because it has some challenges. Let me fast forward it, it will take some time. And these all videos are synchronized, so whatever is happening in one video, all are at the same moment. As we can see, they are trying to make an ellipse crossing each other. Eventually you will see that this tilted ellipse which you are seeing, which you are able to see in the bottom left corner, will be the final ellipse at the end of the experiment also. Why that is happening, I will explain in further slides in the challenges faced. This is the, it will move like this only. It will not be able to come onto the ellipse finally. And these are the turn rates, that is control UK, which we plotted for the experiments. As for the circular motion, we can see that the UK is coming close to 1 for all three agents, but it is not exactly 1 because of the many physical constraints, like the wind or the actuator saturates at the speed, high speeds and all those things. And as for the elliptical motion, we can see there is some uniform phase balancing among all three agents. Now coming to the challenges faced, which is as important as the practical implementation. The first challenge we faced was incompatibility of Crazy Swarm 2, the active marker deck, and QTM for 2 or more than 2 agents. Active marker deck is some other kind of deck which is used with motion capture systems, but we use the passive marker deck due to that. The second one is no support for unicycle model in Crazy Swarm 2 package. Here is when my teammate Shyam contributed. He contributed greatly in making the backend for the unicycle model. Now the third challenge faced is responsible for that tilted ellipse. In simulation, what we did was to calculate the curvature of the ellipse. We simply used ODE in MATLAB. In simulation it works greatly, very fine. But in actual system, that has to be done using the incomplete elliptical integral of second kind, and it has to be done on every iteration. And each iteration takes only 10 milliseconds to send the velocity data to the quadcopter. But in real time, to compute the integral, it takes much more time. That's why, due to that delay, the ellipse is tilted. And as for the future work, we are planning to integrate ground robots with the motion capture system to operate a heterogeneous multi-agent system and apply these distributed control algorithms on outdoor drones in absence of a global sensing system like a mocap system, because that has to be implemented practically. Mocap systems are just for testing and fine-tuning the controls. And we also want to reduce the effect of calculation delays. This is our team. That is me, and the second one is Shyam. Anuj is not present here, and Dr. Anuj Jain, who is our supervisor, and we acknowledge the support from 2 PhD seniors and the project from the MIT. And this is basically appendix. This is the theorem, and these working and all more things. Any questions? Yes, ma'am.